principles and ideas in my head. And the truth is, I don't remember most of it, not in the way they think. When I was a young man at MIT, I watched my fellow students stay up all night before exams, cramming formulas into their heads. They'd write them on their hands, repeat them over and over, test each other in the hallways. And the next morning, they'd march into that exam room like soldiers going to battle, hoping desperately that nothing would fall out of their heads before they could write it down on paper. A week later, if you asked them the same question, they'd look at you with blank faces. The information was gone, evaporated, as if they'd never learned it at all. I remember one particular exam in my junior year, advanced calculus. The fella sitting next to me, brilliant guy, worked harder than anyone I knew, had spent 2 weeks memorizing theorems and proofs. He had flashcards, study groups, the whole works. I'd see him in the library at midnight muttering formulas to himself. The day of the exam, he froze. He could remember the first line of a proof, but not where it went. He knew there was a theorem that applied, but couldn't quite recall its exact statement. He'd built a house of cards, and when one card slipped, the whole thing came down. 6 months later, I asked him about one of those theorems, just out of curiosity, wondering how he'd approach a problem I was working on, and he looked at me like I was speaking a foreign language. It was all gone. I did something different, though I didn't realize it was different at the time. I just couldn't help myself. You see, I had this problem. I needed to understand where things came from. Not just what they were, but why they were. And that changed everything. Let me tell you what I mean. In my sophomore year, we were learning Maxwell's equations. Beautiful things. Really, 4 equations that describe all of electricity and magnetism. My classmates would write them down, stare at them, try to burn them into their memory. But I couldn't do that. I'd look at one of those equations and I'd think, why does it look like that? Where did Maxwell get this from? And I'd have to work backward, tracing the reasoning, until I could see the whole path from the simple experiments with magnets and wires all the way up to this elegant mathematical statement. It took longer, much longer. Sometimes I'd spend an entire evening just understanding one equation while my roommate memorized all 4 and went to bed. He'd shake his head at me, tell me I was wasting time, that we had an exam in 3 days and I was still fiddling around with the basics. But here's the thing, I never forgot those equations. Not because I have a good memory, but because I didn't memorize them at all. I understood them. There's a world of difference between those two things. You see, memory is a funny thing. We think of it like a filing cabinet, where you put information in and hope you can find it again when you need it. But that's not how it really works. Real memory, the kind that lasts, the kind that's useful, isn't storage at all. It's reconstruction. You're not pulling out a file. You're rebuilding the idea from pieces you understand. Think about your own life for a moment. You remember how to get to your friend's house, don't you? But you're not remembering a list of instructions like, turn left at the 3rd Street, go 0.4 miles, turn right. No, you remember landmarks, feelings, the logic of the route. You remember that big oak tree, the yellow house on the corner, the fact that you're heading toward the river. And from those pieces, you reconstruct the path every time. You couldn't forget it if you tried, because you're not storing it, you're understanding it. Or think about something simpler. You know how to make a cup of coffee, right? But you've never memorized the steps. You don't recite to yourself, first fill the kettle, second boil the water, third put coffee in the cup. You just understand the logic of it. Hot water, coffee, mix them together. The exact sequence emerges from understanding what you're trying to do. And because you understand the purpose, extracting flavor from coffee grounds with hot water, you can adapt. If you don't have a kettle, you can use a pot. If you don't have a cup, you can use a mug. Understanding is flexible. Memorization is rigid. That's what I learned to do with physics, and later with everything else I wanted to truly know. I didn't try to remember. I tried to understand so deeply that forgetting became impossible. Let me give you a real example from my work. When I was at Los Alamos during the war, we were working on some very complex calculations for the atomic bomb project. Horrifying thing, really, but that's another story. The point is, we had these incredibly complicated integrals to solve nasty things that would take pages and pages of algebra to work through. My colleagues would solve them once, carefully write down every step in their notebooks, and then refer back to those notebooks whenever they needed the result. I did it differently. Every single time I needed one of those integrals, I would solve it again from scratch. People thought I was insane. You already did this last week, they'd say. Just look at your notes, but I wouldn't. I'd work through it again, and often I'd find a different path, a cleaner way to reach the answer. And something strange happened after a while. These solutions that took me an hour the first time would take me 20 minutes, then 10, then 5. Not because I was remembering the steps, but because I was understanding the structure. I was seeing the pattern underneath. I started to recognize when a certain substitution would work, not because I'd memorized, use this substitution for this type of problem, but because I could feel how the equations wanted to move. It's hard to explain, but it's like knowing how to dance. You don't remember the steps. You feel the music and your body knows what to do. There was one integral in particular, a really nasty one involving exponentials and oscillating functions that kept coming up in different contexts. The first time I solved it, it took me most of an afternoon. Lots of false starts, integration by parts, clever tricks. The second time it appeared, I started fresh again. This time I found a slightly different approach, and it only took an hour. The third time, I suddenly saw a symmetry I'd missed before, and the whole thing collapsed into something much simpler. By the 10th time, I could practically write down the answer, but not because I'd memorized it. I'd internalized the structure so deeply that solving it felt like answering, what's 2 plus 2? The human brain is remarkable at pattern recognition. We're built for it. We see faces in clouds, hear words in random noise, find meaning in chaos. That's our gift, but we waste it when we try to use our brains like computers, storing raw data. Computers are wonderful at that, we're not. What we're wonderful at is finding connections, seeing relationships, building webs of meaning. So here's what I discovered. If you want to remember something forever, don't try to remember it. Instead, connect it to things you already understand. Build it into your web of knowledge so thoroughly that it becomes part of how you think. When I learned quantum mechanics, truly learned it, not just memorized it. I spent months playing with toy problems. Simple systems, simpler than anything you'd see in a real exam. A particle in a box, a harmonic oscillator. I'd solve them in every way I could think of. I'd draw pictures, make analogies, try to explain them to myself in plain English. And slowly, the principles became part of me. They weren't facts I remembered. They were ways of thinking I had absorbed. I remember one night, lying in bed, unable to sleep because I was thinking about the uncertainty principle. Not the formula, anyone can memorize that, but what it really means. I thought about trying to measure where an electron is. To see it, you need light. But light has momentum, and when it hits the electron, it gives it a kick. The harder you try to pin down the position, the bigger the kick, the more uncertain the momentum becomes. It's not a limitation of our instruments. It's built into the fabric of reality. Position and momentum are complementary ways of describing the same thing, and you can't have both perfectly at once. When I finally felt that, not just knew it, but felt it, I could never forget it. It became part of how I see the world. There's a test I've always used, and I recommend it to anyone who wants to really know something. I call it the Explain It Simply test. Here's how it works. After you think you've learned something, try to explain it to someone who doesn't know it, not using the technical words you just learned. Not by repeating what your teacher said, but in your own words, using everyday analogies and simple language. If you can't do this, you don't understand it. Not really. You've only memorized a sophisticated way of talking about it. And that's the trap that catches so many bright people. They learn the language of a subject, they learn to use the right words in the right order, and they mistake that fluency for understanding. But it's not the same thing at all. I remember when I was learning about entropy and thermodynamics. I could recite the definition. Entropy is a measure of disorder in a system. I could write down the equations, manipulate them, solve problems. But one day, someone asked me to explain it without using any technical terms, and I couldn't. I tried, and it all came out as gibberish. That's when I knew I didn't really understand it. So I went back and thought about it differently. I thought about a drop of ink in water, spreading out. I thought about a messy desk and the natural tendency of things to spread out and mix up. I thought about ice melting in a glass of water. Why does it always go that direction? Why doesn't the water freeze and the ice cube get hotter? I thought about information and certainty. What does it mean for something to be ordered? If I have all the molecules of a gas in one corner of a room, I know where they are. That's information. When they spread out, I've lost that information. The entropy increased. And gradually, I built up a real understanding that didn't depend on the formula. After that, I never had to remember what entropy meant. I knew it. More than that, I could feel it. I could look at any system and have an intuition about what would happen to its entropy. Not because I'd memorized rules, but because I understood the principle. This is why teaching is such a powerful tool for learning. When you try to teach something, you're forced to confront the gaps in your understanding. The questions people ask, often simple questions, reveal where you're relying on memorization instead of understanding. I learned more physics from teaching it than I ever learned from studying it. Every time a student asked me why instead of what, I had to either know the answer or admit I didn't. And admitting I didn't know was often the beginning of really learning. I taught introductory physics for years, and every single semester, some student would ask a question that stopped me in my tracks. Simple questions, usually. Why does a heavier object not fall faster? Why is the sky blue? What actually is energy? And I'd realized that I'd been using these words, manipulating these concepts, but I'd never really thought deeply about the fundamental question they were asking. Those moments were gifts. They forced me to go back and think more carefully, to build a better understanding. There was one student, quiet girl, sat in the back, who asked me why we use different formulas for momentum in relativity versus classical mechanics. I started to give her the standard explanation about how the equations change at high speeds, but she interrupted me. "No," she said. "I mean, why? What's really different?" And I realized I'd been teaching the formulas without teaching the insight, so I started over. I talked about how our everyday intuition about adding velocities breaks down. I talked about what it means for the speed of light to be constant for all observers. I talked about how momentum has to be redefined to maintain conservation laws when these weird things start happening. By the end, I'd understood relativity better than I had before she asked the question. There's something else I discovered, though it took me years to articulate it. Understanding isn't a destination, it's a process. You don't learn something once and then you're done. You come back to it again and again, each time from a different angle, and each time you understand it a little more deeply. I must have learned classical mechanics, Newton's laws, and all that at least a dozen times in my life. Once in high school, again in college, again in graduate school, then again when I taught it, and then again when I had to explain it for lectures or write about it. And every single time, I learned something new. Not new facts, the laws of motion haven't changed, but new understanding, new connections, new ways of seeing why things had to be that way. The first time I learned Newton's second law, force equals mass times acceleration, I just memorized it. It was a formula you used to solve problems. The second time, I understood it as a definition of force. The third time, I saw how it connected to conservation of momentum. The fourth time, I realized it was really a statement about how systems respond to constraints. Each layer of understanding made the previous layers richer, and none of it required memorization because each new insight was built on genuine comprehension of what came before. This is perhaps the most important thing I can tell you about remembering. The act of forgetting and relearning is not a failure, it's the method. Every time you reconstruct an idea from pieces you understand, you strengthen those connections. You make the pattern more clear. You see more of the structure. I used to work problems over and over, not because I didn't know how to solve them, but because each time through, I'd see something I'd missed before. Maybe I'd noticed that this equation has the same form as one from a different area of physics. Maybe I'd realize that the reason this step works is connected to some deeper principle. These insights don't come from memorizing. They come from doing, from playing, from thinking. There was a whole summer when I just played with special relativity problems. I'd make up scenarios, a train moving past a station, light bouncing between mirrors, twins going on journeys, and I'd work out what different observers would see. Not for any exam, not for any practical purpose, just because I wanted to feel how relativity worked. And after that summer, relativity wasn't something I'd learned. It was something I lived in. I could close my eyes and visualize events in space-time, see how different observers slice up that space-time into their own notions of space and time. You can't memorize that kind of intuition. You can only build it. You know, there's a joy in this approach that I think we often lose in our obsession with efficiency. We want to learn something once and be done with it. Check the box, move on to the next thing. But real understanding is playful. It's curious. It's willing to spend an afternoon just thinking about why things work the way they do. Not because you'll be tested on it, but because it's interesting. I remember sitting in my backyard one summer, watching water spiral down a drain, and spending an hour just thinking about why it spirals. I already knew the answer, angular momentum, Coriolis effect, all that. But I wanted to really feel it, to see it in my mind, to understand it from the water's point of view. Was that a waste of time? In terms of productivity, maybe. But that hour of thinking probably did more for my understanding of fluid dynamics than a week of reading textbooks would have done. Or I'd watch my kids play on a swing set and think about pendulums. Not the equations, I knew those, but the physical intuition. Why does pushing at just the right moment make them go higher? What's really happening with energy transfer? How does the system know what its natural frequency is? I'd push them and feel the rhythm and think about resonance, and suddenly I'd understand something about oscillating systems that I'd never gotten from textbooks. This is what I mean when I say I don't remember things. I don't have them stored away in some mental filing cabinet. Instead, I have this landscape of understanding in my mind. And when I need something, I navigate through that landscape. I reconstruct the idea from principles I know, from patterns I've seen before, from connections that make sense to me. And here's the beautiful part. Once you build this kind of understanding, it becomes almost impossible to forget. Not because you're trying to hold on to it, but because it's woven into the fabric of how you think. You'd have to unlearn how to see patterns, how to make connections, how to think, and that's not something you can forget. I suppose what I'm really describing is the difference between knowledge and wisdom, though those are awfully grand words. Knowledge is having the right answer stored somewhere. Wisdom is being able to figure out the right answer when you need it. Knowledge is remembering that force equals mass times acceleration. Wisdom is looking at a child on a swing and understanding, really understanding, why pushing at the right moment makes them go higher. And the path to this kind of wisdom isn't fast. It isn't efficient. It doesn't fit well on a syllabus or a study plan. It's messy and personal and sometimes frustrating. But it's also permanent. It's yours in a way that memorized facts never are. I think about the difference between learning a piece of music and memorizing it. You can memorize the notes, this finger here, that finger there, this rhythm, that dynamic. But if you lose your place, you're lost. You have to start over from the beginning or from some other anchor point you've memorized. But if you understand the music, the harmony, the melody, the structure, the emotional arc, you can never really be lost. You know where you are because you feel where you are. And if you make a mistake, you can improvise, adapt, find your way back. You're not executing a memorized sequence. You're creating something you understand. That's how I want to know things. Not as a sequence of steps to execute, but as a structure I understand well enough to improvise within, to adapt, to see from different angles. So if you're trying to learn something, really learn it, not just pass a test on it. Here's my advice. Slow down. Don't rush to memorize. Instead, ask why. Ask where it comes from. Try to explain it to yourself in the simplest possible terms. Play with it. Turn it around in your mind. Connect it to things you already know. And when you forget it, because you will forget it, don't panic. Go back and rebuild it. Each time you do, you're not just remembering. You're deepening your understanding. Make up your own examples. Don't just work the problems in the book. Create problems for yourself. Ask what-if questions. What if this parameter was bigger? What if that force was reversed? What if I changed this assumption? Each question leads you deeper into the structure of what you're learning. And be patient with yourself. Understanding takes time. It's not linear. Some days you'll feel like you're getting nowhere. Then suddenly, maybe in the shower or on a walk, something will click and you'll see it all differently. That's not a magic moment of inspiration. It's your brain working in the background, making connections, finding patterns. Trust that process. There's a humility in this approach, I think. It means admitting that you don't really know something just because you can recite it. It means being willing to say, I don't understand this yet, instead of pretending you do. But it also means trusting that if you put in the effort to truly understand, the remembering will take care of itself. I've spent my whole life learning things, and the older I get, the more I realize how little I actually know. But what I do know, I really know. Not because I have a great memory, but because I built each piece of understanding carefully, connecting it to everything else I know, until it became part of how I see the world. And that's what makes it worth it in the end. Not the facts you can recite, but the way understanding changes how you see things. When you really understand something, the world becomes richer. You see patterns you missed before. You make connections you couldn't see. Everything becomes more interesting because you have more ways of thinking about it. That's the hidden formula, if there is one. Don't try to remember. Try to understand. The rest follows naturally, like water running downhill. And that's not a trick or a hack, it's just how the mind works.